So in that space on the top of page 443, we're going to draw we're going to draw a picture and we're going to explain what you see in this shaded part before we get to example 1, and we'll do example 1 right after this. So I'm going to create some white space here for us. Sure. Okay. So what I would like you to do is draw an angle in standard position. We're going to just draw it here in quadrant 1. On the top of page 443 on the right there. We're going to draw a picture. Okay? We're going to label this hypotenuse. We're going to make a right angle triangle here. We're going to say there's a point on this line if it kept on going. And that point has an x coordinate and it has a y coordinate. This is an angle in standard position. We're going to use theta for our angle. And we're going to say that the length from the origin here to this point, we're going to use the variable r. So we've got a whole bunch of variables here, 4 different variables. We've got an angle, an x coordinate, a y coordinate, and the length of the hypotenuse of that triangle is r. Theta is just a Greek letter that is often used for measuring angles. So in this triangle, since this point is x comma y, this side would be x, this side would be y. Now, what we want to do is we want to imagine that this point could be anywhere. If this length of the hypotenuse is r, and we just kept rotating it around, all the way around, you could do it with a dotted line here. That's not a bad circle. I'm pretty happy. It would make a circle, right? If you took that radius, went all the way around, it would make a circle. And no matter where we put this point along the outside of the edge, we could always draw a triangle back to the x-axis, which uses our reference angles that we learned about yesterday. We can always make a triangle. Now with that triangle in quadrant 1, we could say that cos of theta, and remember SOHCAHTOA, cos is the adjacent side over the hypotenuse, we would get x over r. And that's what's in that shaded box at the top. And you would have sine of theta, well, the opposite side is y, the hypotenuse is r. And you would have tan of theta is y over x. This is the start of something that you're going to study a lot in grade 12 with sine, cos, and tan and circles. And this is just the start of it. The other thing is if we do a squared plus b squared equals c squared for this triangle, because it's a right triangle, you would get x squared plus y squared equals r squared. And I think they've square rooted both sides and have this written as well. This, when it's written this way, x squared plus y squared equals r squared, is actually the proper way to write an equation of a circle. You know equations of lines, you know equations of parabolas. Those are the things you've graphed so far, up till now, up till grade 11. Here is the equation of a circle, and if we would graph all those points, that would be those dots all the way around. It would make a perfect circle. Yes?
Reminds me of the Pythagorean theorem.
And that's all it is. All the equation of the circle is the Pythagorean theorem, x squared plus y squared equals r squared. You could. If you wanted to graph this into your calculator, we can't yet because there's an x and a y. Some of you have a conics program that will allow you to graph circles, which is pretty cool. You could try to solve for y and put a number in for r. Say you wanted radius. If you want your radius of your circle to be 5, then this would be 25. Okay? If you wanted your radius of your circle to be 3, then r squared would be 9, and it would make your circle bigger or smaller. So this is the beginning idea to notice that triangles and a squared plus b squared equals c squared are related to circles, because you could rotate that anywhere along there and notice that. And now we'll get to go to example 1 and be able to solve this. Now the strategy that we're going to use is going to be a big strategy in trigonometry, which might seem like common sense in trigonometry that it would be a big strategy to draw a triangle. Unfortunately, the textbook doesn't use this strategy. So when you watch, if you go on to Math Excel and look at how they do it, I think that their method is a little bit more confusing in my opinion. Drawing a triangle in trigonometry seems to make sense. So we've got a point, -2, -4. Let's say, well, where is that point? -2, -4 would be right there. You can always draw a line to that point, and it says this is an angle in standard position. Standard position would start from the positive x-axis and go all the way around. Now, in order to get sine, cos, and tan, because those are the 3 trig ratios, here's my standard position angle, theta. I'll keep that in green. I want to find sine of theta, cos of theta, and tan of theta. I remember my ratios. That's going to come in and be very important. But so far, have I drawn a triangle yet? No. Now, with the line that I've drawn, you can draw 2 different triangles. Can you see that you could draw one triangle this way, or you could draw one triangle this way? Both of them will be 90 degrees. This one would have a 90 degree here. This one would have a 90 degree there. So they both make right angle triangles. But this, so to, first of all, to determine which triangle we should draw, you always need to go to the nearest x-axis. Whoops, that's a bad line. There's the nearest x-axis. So this inside becomes your reference angle. Can't see that, I did one of these, theta with an r. That's your reference angle. Always make a triangle with your reference angle, because what we saw yesterday was that reference angles and angles were the same. The only thing different is sometimes they're positive, sometimes they're negative. And what rule did we have to help us remember where things were positive and negative? The cast rule. So let's put that here as well to just help us remember. Right now, we're thinking in quadrant 3, because that's where our terminal arm is. So now I've drawn my triangle. What can I label on my triangle? I know that this side is 2, this side is 4. You can add the negatives if you want. You don't have to when drawing a triangle. And now we can do a squared plus b squared equals c squared. What is the length of this side right here? 16 plus 4 would be 20. Square root of 20. Because I did a squared plus b squared equals c squared. Of course, that's a radical that can be simplified. So we always simplify. Square root of 20 is equal to 2 square root of 5. Nice. So that's our hypotenuse. Now we have to, now that we've drawn our triangle, we use SOHCAHTOA and the cast rule to write the ratios. Sine of theta. Well, sine of theta is opposite over hypotenuse. Here's my reference angle. So the opposite side will be 4. Hypotenuse is 2 root 5. So this would be written as 4 over 2 root 5.
But then we gotta rationalize it.
We're going to have to rationalize it, but before we rationalize it, I also want to look at the cast rule. In quadrant 3, I have a t. What does the t mean for the cast rule in quadrant 3? Only tan will be positive. So what should I do to sine? Make it negative. And yes, since we've learned the radicals unit already, we have to multiply top and bottom by root 5 to simplify. 4 over 2, that fraction can also simplify to 2 and 1. And so in the end, I'm going to get negative 2 root 5 over 5 for sine. You'll notice at the bottom of the page they don't rationalize, just in case this unit was taught prior to the radicals one. But the proper answer and what would be expected on your final exam is that you would rationalize the denominator. There's sine. We also have to do cos. Cos would be adjacent over hypotenuse. So we got 2 over 2 root 5. It'll be negative as well because we're still in quadrant 3. And we have to simplify this. These 2's will simplify to 1's. I'll also multiply by root 5 and root 5 top and bottom. And I'll get negative root 5 over 5. And finally, tan is going to be 4 over 2, which simplifies to 2. And tan is positive, so it'll stay positive. Cosine. The A stands for all of them. All of them are positive in quadrant 1. The T stands for tan, and the S stands for sine. So in quadrant 2, only sine is positive. This one is in quadrant 3, and so only the tangent is positive. I always do a check at the end. I like to label my triangle with positive values. I think of them as lengths. Some people like to make this 2 negative already because they're going back 2 and the 4 negative already because they're going down 4. That's not wrong, but you won't be marked wrong if you measure them as lengths either. I always check in the end, did they rule? Do I have sine and cos negative because it's in quadrant 3 and tan positive because it's in quadrant 3? Yes, Alvaro. What I did is I took 4 divided by 2, and I said that fraction can be simplified. And so I just simplified 4 over 2 is the same as 2 over 1, and I showed the work here. So when later I have that, and now it's 1 times 5 on the bottom. So I was just simplifying my fractions early. You could do that after if you liked. But in our final answer, the fraction needs to be simplified. The denominator can't be a radical. So we simplify that as well. So now we've determined all 3 ratios, sine, cos, and tan. Part B says, find the measure of theta. Using your calculator and looking sine, cos, and tan, all of them will find theta. As far as typing things into my calculator, can you see that the tan one would be the easiest? Yeah. So if I start with tan theta equals 2. Okay. Again, the idea is how do you get rid of tan? The opposite of tan is do tan inverse on both sides. Again, some of you will go right to this step right away. Type that into your calculator, and you get 63.43. Awesome. So now, your calculator always tells you an angle between 0 and 90 because it's used to triangles, right? It's used to triangles, right angle triangles. It'll always tell you 63.4, did you say? Close enough. 63.4 degrees to 1 decimal place. Your calculator always tells you an angle between 0 and 90. If we look at our diagram, have we found the big green theta? No, what did we find? We found the little theta r. So maybe I should put a little reference angle in there, because that's what I found. Now what is my green angle going to be? Does that make sense when you look at your diagram? that you would have to go up to here, which is 180, and then go another 63.4 more. So 243.4 rounded to the nearest degree would be 243 degrees. Okay? That's why the drawing the picture really helps, because here I've got my entire angles theta, and there I have my reference angle. Okay? If you had chosen sine or cos, I would go back to my drawing, and when figuring out your reference angle, maybe you want to make a note. When figuring out the reference angle, which we write with theta r, always use positive values. Because if you figured it out with negative root 5 over 5, your calculator is going to give you a different angle for cos. It's going to tell you, in this case, like 114, something weird like that. This one's going to tell you negative 63.4. So when we're figuring out a reference angle, what we're trying to do is we're trying to go back to the triangle that we drew. We're thinking about this as a regular triangle with positive side lengths. That'll give us this little black angle, reference angle. Then we can go and say, what was the actual angle in quadrant 3? It would be 180 plus that reference angle, which is 63.4. Yes? How do we got it? Yeah, because if we look at our picture, if I started here, I'd go 180 to this, and then I go 63.4 more. Sometimes you'll be in quadrant 2. You'll have to figure out, how would I get to that angle using my reference angle? But every single time you'll be able to use your reference angle to figure out what the actual angle is. So the questions you can do for this one are 6, 10, and 11.